Welcome to a world where science, engineering, and culinary artistry converge at speeds that challenge human perception, where humble tubers harvested from the earth undergo a transformation so precise, so meticulously orchestrated, that the final product, a perfectly golden, impossibly crispy potato chip, represents nothing less than a triumph of modern food manufacturing. This is the story of the contemporary potato chip factory, a cathedral of automation where every second sees dozens of potatoes converted into thousands of snacks, where temperatures are controlled to fractions of a degree, where machines see what human eyes cannot, and where the marriage of agricultural science and industrial engineering produces one of the world's most beloved convenience foods. What you're about to witness isn't simply food production. It's a symphony of interconnected systems, each performing its role with mechanical perfection, each contributing to a final product that must meet exacting standards of flavor, texture, appearance, and shelf stability. From the moment a truck laden with specially cultivated potatoes arrives at the factory's receiving bay to the instant a sealed bag rolls off the packaging line, destined for supermarket shelves thousands of miles away, every single step has been refined, optimized, and perfected through decades of innovation, investment, and relentless pursuit of consistency. Our journey begins not in the factory itself, but in the fields where the story of every chip originates, because not all potatoes are created equal, and the varieties destined for chip production represent a highly specialized subset of the broader potato family. These are chipping potatoes, cultivated specifically for their unique physiological characteristics that make them ideal candidates for transformation into crispy snacks. Unlike the starchy russets you might bake for dinner or the waxy reds you'd toss in a salad, chipping potatoes such as the Snowden, the Atlantic, or the Lamoka varieties possess a precise chemical composition that determines their ultimate fate in the fryer. Critical factor is the ratio of solids to water content and, more importantly, the concentration of reducing sugars, glucose and fructose, within the tuber's cellular structure. When a potato slice enters oil, heated to temperatures exceeding 350 degrees Fahrenheit, any sugars present undergo the Maillard reaction, a complex cascade of chemical transformations between amino acids and reducing sugars that produces browning. In baked goods or roasted meats, this browning is desirable, creating rich flavors and appealing colors. In potato chips, however, excessive sugar content results in dark, unevenly colored chips with bitter, acrid flavors that consumers reject instantly. Therefore, chipping potatoes are bred and cultivated to maintain reducing sugar levels below a critical threshold, typically less than 0.1% by weight, a specification so stringent that growers must monitor soil conditions, irrigation schedules, and storage temperatures with scientific precision. The agricultural science behind these specialized potatoes extends deep into the soil itself, where the chemistry of the growing medium directly influences the final product's quality. Potato plants thrive in slightly acidic soils with pH levels between 5 and 6, rich in organic matter that provides the nitrogen, phosphorus, and potassium essential for robust tuber development. But the mineral composition goes far beyond these primary nutrients. Trace elements such as calcium affect cell wall structure, magnesium plays crucial roles in photosynthesis and starch formation, and sulfur influences protein synthesis and enzymatic activity. Modern potato farmers work closely with agronomists and soil scientists, conducting regular soil analyses that measure not only nutrient levels but also soil texture, drainage characteristics, and microbial populations. The physical structure of the soil matters enormously because potatoes are underground storage organs that require loose, well-aerated growing conditions. Compacted soils produce misshapen tubers with growth defects, while overly sandy soils may not retain sufficient moisture during critical growth periods. Farmers employ sophisticated irrigation systems, often utilizing drip technology or center pivot sprinklers, equipped with soil moisture sensors and weather station data integration, ensuring that water delivery matches the plant's physiological needs at each growth stage, while minimizing waste and preventing the waterlogged conditions that promote rot and disease. Harvesting these specialized potatoes requires machinery that represents the pinnacle of agricultural engineering, massive potato harvesters that dwarf the operators who guide them through the fields. These mechanical behemoths accomplish in hours what would have required weeks of backbreaking manual labor just generations ago. The harvesting process begins with a coulter blade that cuts through the soil ahead of the main share, which then lifts the entire potato-bearing layer of earth onto a series of vibrating webs and chains. These moving surfaces perform a delicate dance, shaking loose the soil while carefully separating the tubers, because bruising or damaging potatoes during harvest creates defects that will only become more apparent during processing. Modern harvesters incorporate cushioned surfaces, adjustable web speeds, and even automated systems that adjust lift depth based on real-time feedback about crop density and soil conditions. As the potatoes emerge from this mechanical excavation, they're elevated onto collection platforms where workers can remove rocks, clods, and the occasional oddly shaped tuber that doesn't meet specifications. These field harvesters, the potatoes move into bulk storage systems or directly onto trucks for transport to the processing facility. And it's here that the cold chain management becomes critical, because the storage temperature of potatoes directly affects their sugar content through a biochemical process called cold-induced sweetening. When potatoes are stored at temperatures below 42 degrees Fahrenheit, the tuber's metabolism shifts, converting starches into sugars as a natural defense against freezing damage. This physiological response, while beneficial for the potato's survival in cold conditions, is disastrous for chip quality as it elevates those problematic reducing sugars that cause dark frying and off flavors. Consequently, commercial potato storage facilities maintain carefully controlled environments, typically holding temperatures between 45 and 50 degrees Fahrenheit, with relative humidity around 95% to prevent moisture loss, while avoiding condensation that could promote bacterial and fungal growth. These storage facilities are architectural marvels in their own right, often capable of holding thousands of tons of potatoes in climate-controlled chambers, equipped with sophisticated ventilation systems that circulate air through the stored tubers, removing the carbon dioxide and heat generated by their continued respiration while delivering fresh oxygen. Some facilities employ controlled atmosphere storage, reducing oxygen levels to slow metabolic processes and extend storage life, while others use chemical sprout suppressants to prevent the emergence of shoots that would drain energy reserves and reduce tuber quality. The logistics of managing this agricultural inventory are staggering, coordinating harvest timing, storage capacity, processing schedules, and transportation to ensure a continuous supply of optimal quality potatoes flowing into the factory 12 months a year, despite the seasonal nature of agricultural production. Now, our potatoes arrive at the factory, transported in specialized trucks that may carry 20 to 30 tons of tubers per load, backing up to receiving bays, where the industrial transformation begins with a process as dramatic as it is efficient. The truck beds are hydraulically tilted to steep angles, sometimes approaching 45 degrees, causing an avalanche of potatoes to cascade into water-filled flumes. Channels constructed from stainless steel or food-grade concrete that use the gentle conveying power of flowing water to transport the tubers into the facility. This water-based reception system serves multiple critical functions simultaneously. It cushions the potato's descent, minimizing impact damage that could cause bruising. It begins the cleaning process, washing away field soil, small stones, and organic debris, and it provides the first stage of density separation, as stones and soil particles sink while potatoes, with their lower specific gravity, float and flow with the current. The volume of water flowing through these flumes is tremendous, measured in thousands of gallons per minute, and it's recirculated through filtration systems that remove suspended solids, maintaining water clarity and quality while minimizing waste. The engineering of these flume systems reflects decades of refinement. The channel angles, water velocities, and flow patterns are optimized to move potatoes efficiently without tumbling them excessively, and the materials are chosen for durability, cleanability, and resistance to the abrasive action of millions of tubers flowing past each day. As the potatoes ride these aquatic conveyor systems deeper into the facility, they encounter the destoner, a remarkably clever device that exploits the principle of specific gravity to separate remaining stones, which are denser than potatoes, from the tubers themselves. In the destoner, the water-potato mixture flows over a sloped, perforated surface, or through a specially designed tank, where agitation and water flow patterns cause heavier materials to settle and be diverted away while potatoes continue forward. The precision of this separation is remarkable. Stones as small as pebbles are reliably removed, protecting downstream equipment from damage and preventing potential hazards to consumers. Following destoning, the potatoes may pass through additional inspection stations where workers or automated vision systems identify and remove tubers that are green, sprouted, rotted, or otherwise unsuitable for processing. Green potatoes contain elevated levels of solanine, a naturally occurring glycoalkaloid that can cause bitterness and, in sufficient quantities, toxicity. So their removal is not merely a quality issue, but a food safety imperative. The next phase brings us to one of the factory's most water-intensive operations, the barrel washer, a rotating cylindrical drum constructed from stainless steel mesh or perforated plate, inclined slightly from horizontal, which tumbles and scrubs the potatoes while spraying them with high-pressure water jets. As the potatoes tumble through this rotating environment, centrifugal force presses them against the drum's walls, while the forward inclination causes them to gradually migrate from inlet to outlet. The mechanical action, potato rubbing against potato, surfaces scraping against the drum's mesh, removes the remaining soil, scrubs away surface blemishes, and even polishes the skin to some degree. The water pressure and spray patterns are carefully engineered to penetrate into crevices and surface irregularities without being so forceful as to damage the tubers. High-volume pumps deliver water at pressures that can exceed 100 pounds per square inch, sufficient to dislodge stubborn soil particles and organic matter. The barrel washer's rotation speed is adjustable, typically ranging from 10 to 30 revolutions per minute, with the optimal speed representing a balance between cleaning effectiveness and gentle handling. Emerging from the barrel washer, the potatoes are substantially cleaner, and the wash water, now laden with soil, organic matter, and dissolved substances, flows to waste treatment systems, where solids are settled or filtered out, and the clarified water may be partially reused or discharged in compliance with environmental regulations. Following this vigorous washing, many facilities employ a secondary, more refined cleaning stage using brush washers, where rotating brushes made from food-grade synthetic bristles provide a gentler but thorough final scrubbing. These brush systems are particularly effective at removing any remaining soil from surface irregularities, eyes, and stem end cavities without the aggressive mechanical action of tumbling. The brushes rotate at high speed, their bristles flexing and conforming to the potato's contours, while water sprays rinse away dislodged debris. The engineering sophistication here includes adjustable brush pressure, variable rotation speeds, and segmented zones with different brush stiffness characteristics to address varying cleaning challenges. After emerging from the brush washers, the potatoes are substantially cleaner than when they arrived, having been subjected to multiple stages of aquatic and mechanical cleaning that have removed virtually all traces of the field from which they came. The most common slicer design used in high-volume chip production is the centrifugal slicer, a rotating device that utilizes centrifugal force to press potatoes against spinning blades. Picture a circular plate, perhaps 4 feet in diameter, rotating at speeds that can exceed 300 revolutions per minute. Mounted around the perimeter of this plate are razor-sharp blades positioned at precise angles and held in place with exacting tolerances. Potatoes are fed into the center of this spinning disc, where they're caught by the centrifugal force and flung outward toward the rotating perimeter. As each potato travels outward, it encounters the blade, which slices through the tuber with such precision that the resulting slice thickness can be controlled to tolerances of a few thousandths of an inch, typically between 50 and 70 thousandths of an inch, depending on the desired final chip characteristics. The metallurgy of these slicing blades represents a specialized branch of materials science. These aren't ordinary steel knives, but rather precision-ground cutting edges, manufactured from high-carbon stainless steel alloys, heat-treated to achieve hardness values exceeding 58 on the Rockwell C scale. This extreme hardness maintains the blade's sharp edge through millions of slicing operations, and the stainless composition resists corrosion in the wet, starchy environment of potato processing. The blade's edge is ground to a precise bevel angle, creating a cutting geometry optimized for the cellular structure of potato tissue. The blades are removable and replaceable, and most facilities employ dedicated maintenance teams who regularly sharpen or replace blades according to schedules determined by slice quality monitoring. Even microscopic blade degradation affects slice uniformity, which in turn affects frying consistency, seasoning adherence, and final product quality. Some advanced slicer designs incorporate automatic blade tensioning systems that maintain optimal blade position and pressure, compensating for wear and thermal expansion, ensuring that the millionth slice of the day meets the same specifications as the first. The physics at play within the centrifugal slicer are fascinating when examined in detail. As the potato travels outward from the center of the spinning disc, it experiences an acceleration that increases with both the rotational velocity and the radius at which it's positioned. This centrifugal acceleration presses the potato firmly against the blade, ensuring consistent contact pressure and clean slicing action. The potato's trajectory isn't simply radial, but follows a complex path influenced by friction against the disc surface, the geometry of the potato itself, and the interactions with other potatoes being processed simultaneously. The slicer can process dozens of potatoes per minute, each one being sliced into dozens of individual chips, meaning that at any given instant, multiple slicing operations are occurring simultaneously around the disc's perimeter. The resulting slices are ejected from the slicer through centrifugal force, flying outward into collection systems or directly onto conveyors that transport them to the next processing stage. These freshly cut potato slices represent a moment of vulnerability in the production process because the act of slicing ruptures countless cells, releasing enzymes and exposing interior tissues to oxygen. Within minutes, enzymatic browning reactions can begin, causing discoloration, and released starches create a sticky surface that causes slices to clump together. To prevent these issues, the slices immediately enter a water bath or pass under high-volume water sprays that rinse away surface starch, gelatinized cellular contents, and dissolved sugars, while simultaneously cooling the slices and slowing enzymatic activity. This rinsing process is more sophisticated than simply spraying water. The water chemistry, temperature, and flow patterns are all controlled variables. Some facilities add food-grade acids such as citric acid to the rinse water, slightly lowering the pH to inhibit enzymatic browning. The temperature is typically maintained below 60 degrees Fahrenheit to slow metabolic processes. The volume and velocity of water flow are calibrated to ensure complete starch removal without being so turbulent as to damage the fragile slices. Following the starch rinse, the slices advance to a dewatering stage, often accomplished through vibrating screens or centrifugal force that removes excess surface water. Removing this water is critical because introducing wet potato slices into hot oil causes violent boiling, oil splashing, and reduced frying efficiency. Excessive surface moisture also increases the energy required to fry the chips and can cause uneven cooking. Dewatering equipment ranges from simple inclined screens that allow gravity and vibration to shed water droplets to sophisticated centrifugal dryers that spin the slices at high speed, using centrifugal force to fling water away from the surfaces. Some facilities employ forced air systems that blow ambient or heated air across the slices, evaporating remaining surface moisture. The goal is to reduce surface moisture content to levels that minimize oil spattering during frying, while avoiding over-drying that could cause the slices to become brittle or develop surface cracks. Now we arrive at the heart of the chip-making process, the technological and thermodynamic centerpiece of the entire operation, the continuous fryer. This is where potato slices undergo their ultimate transformation, where moisture within the cellular matrix flashes to steam, where surfaces dehydrate and crisp, where the Maillard reaction creates golden colors and complex flavors, where a pale, soft, starchy slice becomes the crunchy snack consumers crave. Industrial potato chip fryers are engineering marvels, often measuring 40 to 60 feet in length, resembling massive stainless steel canals filled with churning, bubbling vegetable oil maintained at precisely controlled temperatures. The most common fryer configuration is the continuous belt system, where potato slices are fed onto a submerging conveyor belt that carries them through the oil bath at a controlled speed, emerging at the far end as fully cooked chips. The residence time within the fryer, the duration each slice spends immersed in hot oil, typically ranges from 2 to 4 minutes, depending on slice thickness, desired moisture content in the finished chip, and production speed requirements. The selection of frying oil represents a critical decision with implications for flavor, shelf life, production costs, and nutritional profile. Historically, potato chips were fried in animal fats or partially hydrogenated vegetable oils, but contemporary health concerns regarding trans fats and saturated fats have driven the industry toward oils with more favorable fatty acid profiles. Today's chip manufacturers predominantly use oils such as sunflower, corn, canola, or specially formulated blends designed to balance stability, flavor neutrality, and cost. The ideal frying oil possesses high smoke point, the temperature at which it begins to break down and produce smoke, typically above 400 degrees Fahrenheit, ensuring it can maintain frying temperatures without degradation. It should resist oxidation, the chemical process through which unsaturated fatty acids react with oxygen to form rancid flavors and potentially harmful compounds. Oils high in polyunsaturated fats oxidize more rapidly than those rich in monounsaturated or saturated fats, creating a trade-off between nutritional profile and shelf stability. Many manufacturers employ oil blends that optimize this balance or add natural antioxidants such as tocopherols to extend oil life. Within the fryer itself, temperature management is an exercise in precision thermal engineering. The oil temperature isn't uniform throughout the fryer's volume, but varies in carefully controlled zones. As potato slices enter the fryer, they're typically at ambient temperature, and they carry residual surface moisture despite the dewatering process. This moisture, upon encountering oil at 350 to 375 degrees Fahrenheit, instantly vaporizes, creating vigorous boiling that produces the characteristic bubbling and churning visible at the fryer's surface. This phase change from liquid water to steam requires substantial energy, approximately 1,000 BTUs per pound of water, energy that's drawn from the surrounding oil, causing localized cooling. To compensate, fryers incorporate multiple heating zones with independent temperature controls, ensuring that despite the continuous heat extraction by incoming cold, wet potato slices, the oil temperature remains within the target range throughout the fryer's length. The heating systems themselves are typically either direct-fired burners beneath the fryer or electric heating elements immersed in the oil. With sophisticated temperature sensors and control systems, adjusting heat input in real time based on feedback from multiple thermocouples positioned throughout the fryer volume. Oil management within the fryer represents an ongoing operational challenge and a significant cost factor. As oil is repeatedly used for frying, it undergoes gradual degradation through multiple mechanisms: thermal decomposition from prolonged exposure to high temperatures, hydrolysis from contact with moisture in the potato slices, and oxidation from exposure to air at the fryer's surface. These degradation processes produce free fatty acids, polymerized compounds, and oxidation products that darken the oil's color, increase its viscosity, lower its smoke point, and contribute off flavors to the chips. Manufacturers combat this degradation through continuous or periodic oil filtration systems that remove food particles and some degradation products. By regularly adding fresh oil to replace what's absorbed into the chips or lost to evaporation, and by complete oil changes when quality parameters exceed acceptable limits. Modern fryers incorporate automated oil management systems that monitor oil quality through sensors measuring color, free fatty acid content, total polar materials, or dielectric constant, providing operators with objective data to guide oil maintenance decisions. Some facilities have implemented closed-loop oil systems where degraded frying oil is collected and sold for biodiesel production or other industrial applications, turning a waste product into a revenue stream while supporting sustainability goals. Emerging from the fryer, the chips are extraordinarily hot, typically 180 to 200 degrees Fahrenheit, still containing residual oil that drains away as they travel on conveyors toward cooling stations. The post-frying conveyor systems are often perforated or made of mesh to allow continued oil drainage, with collection trays beneath capturing this excess oil for return to the fryer or to waste oil management systems. The chips at this stage are fragile, their glassy structure prone to fracturing under mechanical stress, so handling systems are designed to minimize turbulence and impact. The cooling process itself is critical because chips packaged while still warm would generate condensation as they cooled within sealed bags, creating moisture that would destroy crispness and potentially enable microbial growth. Cooling is typically accomplished through forced air convection, with large fans blowing ambient or temperature-controlled air across the chips as they travel on extended conveyor systems. Some facilities use cooling tunnels where airflow, temperature, and humidity are precisely controlled to optimize cooling rates while preventing moisture absorption from the atmosphere. The residence time in the cooling zone may be 5 to 15 minutes, sufficient for chips to reach temperatures suitable for seasoning and packaging. As the chips cool and stabilize, they approach one of the factory's most fascinating technological zones, the quality control inspection systems. Contemporary potato chip factories employ optical sorting machines that represent the marriage of advanced imaging technology, high-speed computing, and precision pneumatics. These systems, sometimes called color sorters or vision sorters, examine every single chip that passes through the line at speeds that can exceed 10 chips per second per scanning channel. The technology centers on high-resolution cameras, often incorporating multiple spectral bands, including visible light and near-infrared wavelengths, that capture images of chips as they fall or travel on conveyors through the inspection zone. Each chip's image is analyzed in real time by sophisticated algorithms that evaluate color uniformity, looking for chips that are too dark, indicating excessive frying or high sugar content, or too light, suggesting insufficient cooking. The systems also detect defects such as green spots from chlorophyll in tubers exposed to light during growth, black spots from bruising or enzymatic discoloration, and foreign material contamination. When the vision system identifies a defective chip, it triggers an air jet, a precisely timed blast of compressed air lasting mere milliseconds that ejects the offending chip from the product stream into a reject bin. The accuracy of these systems is remarkable, reliably identifying and removing defects smaller than a quarter-inch in diameter while operating at speeds that process thousands of pounds of chips per hour. The artificial intelligence underlying modern optical sorting systems has evolved dramatically in recent years, moving beyond simple color thresholds to employ machine learning algorithms trained on hundreds of thousands of chip images, representing both acceptable product and various defect categories. These neural networks learn to recognize subtle patterns, color gradations, and shape characteristics that correlate with quality attributes, achieving discrimination capabilities that rival or exceed human inspectors while operating tirelessly and consistently. Some systems incorporate feedback loops where chips flagged by the sorter are periodically sampled and evaluated by human quality technicians, the algorithm to continuously refine its performance. The computing power required for this real-time image processing and decision-making is substantial. Industrial vision systems incorporate dedicated processing hardware, including GPUs optimized for parallel processing of image data, with processing latencies measured in milliseconds to ensure decisions are made before chips pass beyond the rejection zone. Beyond the optical sorters, many facilities employ additional quality checks, including metal detectors and X-ray inspection systems. Metal detectors, based on electromagnetic induction principles, identify any metallic contamination that might have entered the product stream through equipment wear or foreign object introduction. When metallic objects pass through the detector's electromagnetic field, they create disturbances that trigger alarms and automatic rejection systems. X-ray inspection systems provide complementary capabilities, detecting foreign materials with different densities than potato chips, including glass, stone, dense plastics, and some non-metallic contaminants that would be invisible to optical systems. The X-ray technology operates by passing low-energy X-rays through the product stream and measuring absorption patterns with detector arrays, with sophisticated software analyzing these patterns to identify anomalies. These safety-focused inspection systems represent critical controls ensuring that products reaching consumers are free from physical hazards that could cause injury. Now the chips, having been cooked, cooled and inspected, advance toward the seasoning station, where they'll acquire the distinctive flavors that differentiate various product offerings. The base potato chip possesses a pleasant, slightly nutty flavor from the fried potato itself, enhanced by the absorbed oil, but modern consumers expect diverse flavor experiences ranging from simple salted varieties to complex profiles involving multiple spice blends, cheese powders, and flavor compounds. The mechanical process of applying seasonings to potato chips presents engineering challenges because the chips are fragile, irregular in shape, and need to be coated uniformly with powder seasonings that naturally tend to settle or clump. The most common seasoning application method employs rotating drums, cylindrical vessels inclined slightly from horizontal that tumble the chips while seasoning is sprayed or dusted onto them. As chips tumble through the drum, they present different surfaces to the seasoning applicators, and the tumbling action helps distribute seasoning across the population of chips. The drums rotate at carefully controlled speeds, fast enough to achieve mixing and tumbling, but not so fast that chips are damaged through excessive mechanical action. The seasonings themselves are engineered products, often complex formulations developed by flavor chemists who combine salt, spices, dried cheese or dairy products, monosodium glutamate or other flavor enhancers, acids such as citric acid or malic acid for tanginess, sugars for sweetness, or to participate in browning reactions, and proprietary flavor compounds synthesized to replicate specific taste profiles. These seasoning blends are typically fine powders with carefully controlled particle size distributions. Particles must be small enough to adhere to the chip surfaces and provide uniform flavor distribution, but not so fine that they create dust clouds or fail to adhere. The moisture content of seasoning blends is critical because excess moisture causes caking and clumping, while insufficient moisture results in poor adhesion to the chip's oily surface. Some advanced seasoning systems employ electrostatic charging of the seasoning powder, creating an electrical potential difference between the chips and the seasoning particles that enhances adhesion through electrostatic attraction, similar to principles used in powder coating applications in other industries. The spray application method offers advantages in terms of seasoning, distribution uniformity, and the ability to apply wet seasonings or flavor compounds that don't exist in powder form, but it adds complexity and requires additional control over spray droplet size, oil temperature, and application rates. Following seasoning, the chips may pass through additional quality inspection points where automated vision systems verify seasoning coverage uniformity, checking that chips aren't excessively coated or bare. Some facilities employ laser-based sensors that measure powder coverage by analyzing light reflection patterns from chip surfaces. These quality checks ensure product consistency and help identify issues with seasoning application equipment before significant quantities of out-of-specification product are produced. The final major operation before consumer purchase is packaging, and this seemingly simple task represents a pinnacle of engineering sophistication where high-speed automation, material science, and precision control converge. Potato chips present unique packaging challenges. They're fragile and easily broken. They're sensitive to oxygen and moisture, which cause staleness and texture degradation. And their irregular shapes and low bulk density mean that packages are mostly air by volume. Modern chip packaging addresses these challenges through multiple innovations, starting with the packaging material itself. Today's chip bags aren't simple plastic film, but rather sophisticated multi-layer laminates combining several distinct materials, each contributing specific properties. A typical structure might include an outer layer of oriented polypropylene or polyester, providing printability, abrasion resistance, and structural strength. A middle barrier layer of metallized film or aluminum foil, preventing oxygen and moisture transmission, and an inner sealant layer of polyethylene, providing heat sealability and food contact compliance. These layers, each just microns thick, are bonded together through lamination processes, creating a composite structure with properties superior to any single material. The barrier performance of these films is extraordinary. Oxygen transmission rates can be less than 1 cubic centimeter per square meter per day, and moisture vapor transmission rates below 1 gram per square meter per day, providing the protection necessary for shelf lives measured in months. The packaging machines themselves are mechanical marvels, operating at speeds that can exceed 100 bags per minute. The process begins with film unrolling from large master rolls, passing through printing stations if graphics aren't pre-printed, then entering the form-fill-seal machine, where the magic happens. In vertical form-fill-seal systems, the most common configuration for chip packaging, the flat film is drawn over a forming tube that shapes it into a cylinder with overlapping edges. These edges are heat-sealed together, creating a continuous tube of film, open at both ends. The chips, transported by conveyor systems or vibratory feeds, flow down through the center of this tube while simultaneously, at the bottom of the machine, intermittent sealing jaws close across the tube, creating the bottom seal of one package and the top seal of the package below it simultaneously. A cutting mechanism, often a heated wire or knife, separates the completed package from the continuous tube. This entire sequence, forming, filling, sealing, and cutting, occurs at remarkable speeds with mechanical precision, driven by servo motors and controlled by programmable logic controllers that coordinate dozens of movements with millisecond timing. Before the bags are sealed, most chip manufacturers employ a critical technology called nitrogen flushing, or modified atmosphere packaging. Oxygen is the enemy of chip freshness, driving lipid oxidation reactions that create rancid flavors and destroying crispness through moisture absorption. To combat this, the packaging machines inject nitrogen gas into the bags just before sealing, displacing atmospheric air and creating a protective atmosphere that's typically 99% nitrogen. This nitrogen serves a dual purpose. It excludes oxygen, dramatically extending shelf life, and it acts as a cushion, inflating the bag and providing mechanical protection during shipping and handling that reduces chip breakage. The nitrogen injection systems are precisely calibrated to deliver consistent gas volumes, maintaining the characteristic puffy appearance of chip bags while ensuring adequate product protection. Some facilities monitor residual oxygen levels in sealed packages using inline sensors that measure oxygen concentration through the packaging film or by sampling and analyzing headspace gas composition from random packages. The filled and sealed bags then advance to weighing and quality verification stations. While the packaging machines incorporate load cells or other weight-sensing systems that attempt to deliver the target chip quantity to each bag, verification checks ensure compliance with weight declarations and identify packages that are underfilled or overfilled. Automated checkweighers pass each package over high-precision load cells that measure weight to fractions of a gram, with reject mechanisms diverting packages outside acceptable weight ranges. Metal detectors and X-ray systems provide final safety checks, ensuring no contamination has occurred during the packaging process. Vision systems inspect seal integrity, checking that heat seals are complete and properly formed, as defective seals would allow atmosphere infiltration and product degradation. The packaged chips now move toward case packing and palletizing operations where individual bags are grouped into shipping cases, and these cases are stacked onto pallets for distribution. Case packing systems range from manual operations where workers hand-load bags into corrugated cardboard cases to fully automated systems employing robotic pick-and-place mechanisms. The robots, typically articulated arm designs with specialized end effectors, grasp individual bags or groups of bags and position them precisely within cases, traveling on conveyor lines. Vision guidance systems help robots locate and orient bags correctly, while force sensors ensure gentle handling that doesn't crush chips. Case erectors automatically fold flat corrugated blanks into three-dimensional cases, while case sealers apply tape or glue to secure flaps after loading, all synchronized with the robot's packing cycle through central control systems. Palletizing represents the final automated handling stage, where filled cases are stacked in stable patterns onto wooden or plastic pallets for transportation. Automated palletizers, either robotic systems or conventional layer-forming machines, create pallet loads according to programmed patterns that optimize stability, stack height, and pallet utilization. A typical pallet load might contain 40 to 60 cases stacked 6 to 8 layers high, representing hundreds or thousands of individual chip bags. Stretch wrapping machines then envelop completed pallet loads in multiple layers of stretchable plastic film, securing the load and protecting it from dust and moisture during storage and transit. The wrapped pallets travel to the warehouse, where sophisticated inventory management systems track product by production date, flavor, and destination, with warehouse management software optimizing storage locations and retrieval sequences to support first in, first out rotation and efficient order fulfillment. The logistics of distributing these finished products represent the final chapter in our potato chip journey, connecting the factory to the vast network of retailers, wholesalers, and food service operators who ultimately place chips within reach of consumers. Modern factories ship product through complex distribution networks involving company-owned distribution centers, third-party logistics providers, and direct-to-store delivery systems. Temperature-controlled transportation isn't typically required for shelf-stable chips, but protection from physical damage and extreme temperatures remains important. Trucks and shipping containers are loaded carefully to prevent crushing, and in regions with extreme climates, temperature-controlled transport might be employed during summer months to prevent oil migration and textural changes that can occur when products experience sustained high temperatures. The supply chain visibility enabled by modern logistics technology allows manufacturers to track individual pallet loads from factory to store, monitoring transit times, environmental conditions, and delivery confirmations through barcode scanning, RFID tags, and GPS-enabled fleet management systems. When those packages finally reach retail shelves or vending machines or convenience store displays, they represent the culmination of an extraordinary journey spanning agricultural fields, industrial processing facilities, sophisticated quality systems, and complex logistics networks. The consumer who casually reaches for a bag of chips and tears it open experiences the sensory payoff of this vast industrial effort. The satisfying crackle of the bag opening, the rush of nitrogen-preserved aroma, the first bite delivering that perfect combination of crunch and flavor that has made potato chips one of the world's favorite snacks. That crunch, scientifically speaking, is the result of the dehydrated, glassy cellular structure fracturing under pressure, creating sound waves that travel through bone conduction to the ear, providing sensory feedback that's much about texture perception as taste. The flavor is a complex sensory experience, combining the Maillard reaction products from frying, the nutty notes from the potato itself, the richness from absorbed oil, and whatever seasonings have been applied, all perceived through combinations of taste receptors on the tongue and olfactory receptors in the nasal passages. The potato chip industry continues to evolve with technological advancement, changing consumer preferences, and heightened awareness of nutrition, sustainability, and food system impacts. Manufacturers invest continuously in research and development, exploring alternative cooking methods such as baking or air frying that might reduce oil content, investigating novel seasonings and flavor profiles that address global taste preferences, and developing packaging solutions with reduced environmental footprints through material reduction, recyclability improvements, or biodegradable alternatives. Automation advances steadily with increasing deployment of robotics, artificial intelligence, and predictive maintenance systems that enhance efficiency and consistency while reducing labor requirements. Sustainability initiatives address water usage, energy consumption, and waste generation throughout the manufacturing process, with many facilities implementing water recycling systems, heat recovery from fryer exhaust, and programs to convert processing waste into animal feed, biogas, or compost. The agricultural supply chains are evolving too, with increasing adoption of precision agriculture technologies, development of potato varieties with improved processing characteristics or enhanced nutritional profiles, and programs promoting sustainable farming practices that protect soil health and minimize environmental impacts. In examining this industrial ecosystem from agricultural field to consumer snack, we've witnessed a remarkable demonstration of how modern food manufacturing integrates multiple scientific disciplines, engineering specializations, and technological systems to transform raw agricultural commodities into consistent, safe, convenient products available globally at affordable prices. The humble potato chip, often dismissed as simple junk food, reveals itself upon closer examination as a triumph of applied science, precision engineering, and supply chain orchestration. Every aspect of its production reflects decades of accumulated knowledge, continuous improvement, and substantial capital investment in facilities, equipment, and expertise. The factories that produce these snacks aren't merely manufacturing plants, but rather technological showcases where agricultural science, mechanical engineering, chemical engineering, food science, quality systems, and logistics expertise converge in service of a singular goal: delivering to consumers the perfect chip every time, everywhere. Vision systems inspect seal integrity, checking that heat seals are complete and properly formed, as defective seals would allow atmosphere infiltration and product degradation. The packaged chips now move toward case packing and palletizing operations, where individual bags are grouped into shipping cases, and these cases are stacked onto pallets for distribution. Case packing systems range from manual operations where workers hand-load bags into corrugated cardboard cases to fully automated systems employing robotic pick-and-place mechanisms. The robots, typically articulated arm designs with specialized end effectors, grasp individual bags or groups of bags and position them precisely within cases traveling on conveyor lines. Vision guidance systems help robots locate and orient bags correctly, while force sensors ensure gentle handling that doesn't crush chips. Case erectors automatically fold flat corrugated blanks into three-dimensional cases, while case sealers apply tape or glue to secure flaps after loading, all synchronized with the robot's packing cycle through central control systems. Palletizing represents the final automated handling stage, where filled cases are stacked in stable patterns onto wooden or plastic pallets for transportation. Automated palletizers, either robotic systems or conventional layer-forming machines, create pallet loads according to programmed patterns that optimize stability, stack height, and pallet utilization. A typical pallet load might contain 40 to 60 cases stacked 6 to 8 layers high, representing hundreds or thousands of individual chip bags. Stretch wrapping machines then envelop completed pallet loads in multiple layers of stretchable plastic film, securing the load and protecting it from dust and moisture during storage and transit. The wrapped pallets travel to the warehouse, where sophisticated inventory management systems track product by production date, flavor, and destination, with warehouse management software optimizing storage locations and retrieval sequences to support first-in, first-out rotation and efficient order fulfillment. The logistics of distributing these finished products represent the final chapter in our potato chip journey, connecting the factory to the vast network of retailers, wholesalers, and food service operators who ultimately place chips within reach of consumers. Modern factories ship product through complex distribution networks involving company-owned distribution centers, third-party logistics providers, and direct-to-store delivery systems. Temperature-controlled transportation isn't typically required for shelf-stable chips, but protection from physical damage and extreme temperatures remains important. Trucks and shipping containers are loaded carefully to prevent crushing, and in regions with extreme climates, temperature-controlled transport might be employed during summer months to prevent oil migration and textural changes that can occur when products experience sustained high temperatures. The supply chain visibility enabled by modern logistics technology allows manufacturers to track individual pallet loads from factory to store, monitoring transit times, environmental conditions, and delivery confirmations through barcode scanning, RFID tags, and GPS-enabled fleet management systems. When those packages finally reach retail shelves or vending machines or convenience store displays, they represent the culmination of an extraordinary journey spanning agricultural fields, industrial processing facilities, sophisticated quality systems, and complex logistics networks. The consumer who casually reaches for a bag of chips and tears it open experiences the sensory payoff of this vast industrial effort. The satisfying crackle of the bag opening, the rush of nitrogen-preserved aroma, the first bite delivering that perfect combination of crunch and flavor that has made potato chips one of the world's favorite snacks. That crunch, scientifically speaking, is the result of the dehydrated, glassy cellular structure fracturing under pressure, creating sound waves that travel through bone conduction to the ear, providing sensory feedback that's as much about texture perception as taste. The flavor is a complex sensory experience combining the Maillard reaction products from frying, the nutty notes from the potato itself, the richness from absorbed oil, and whatever seasonings have been applied, all perceived through combinations of taste receptors on the tongue and olfactory receptors in the nasal passages. The potato chip industry continues to evolve with technological advancement, changing consumer preferences, and heightened awareness of nutrition, sustainability, and food system impacts. Manufacturers invest continuously in research and development, exploring alternative cooking methods such as baking or air frying that might reduce oil content, investigating novel seasonings and flavor profiles that address global taste preferences, and developing packaging solutions with reduced environmental footprints through material reduction, recyclability improvements, or biodegradable alternatives. Automation advances steadily with increasing deployment of robotics, artificial intelligence, and predictive maintenance systems that enhance efficiency and consistency while reducing labor requirements. Sustainability initiatives address water usage, energy consumption, and waste generation throughout the manufacturing process, with many facilities implementing water recycling systems, heat recovery from fryer exhaust, and programs to convert processing waste into animal feed, biogas, or compost. The agricultural supply chains are evolving too, with increasing adoption of precision agriculture technologies, development of potato varieties with improved processing characteristics or enhanced nutritional profiles, and programs promoting sustainable farming practices that protect soil health and minimize environmental impacts. In examining this industrial ecosystem from agricultural field to consumer snack, we've witnessed a remarkable demonstration of how modern food manufacturing integrates multiple scientific disciplines, engineering specializations, and technological systems to transform raw agricultural commodities into consistent, safe, convenient products available globally at affordable prices. The humble potato chip, often dismissed as simple junk food, reveals itself upon closer examination as a triumph of applied science, precision engineering, and supply chain orchestration. Every aspect of its production reflects decades of accumulated knowledge, continuous improvement, and substantial capital investment in facilities, equipment, and expertise. The factories that produce these snacks aren't merely manufacturing plants, but rather technological showcases where agricultural science, mechanical engineering, chemical engineering, food science, quality systems, and logistics expertise converge in service of a singular goal: delivering to consumers the perfect chip every time, everywhere.